Good. All right. Welcome, everybody. Thanks for coming today. Today, we had the pleasure of being hosting Oier. He's a lead research scientist for robot learning and foundation models at Microsoft, where his research focuses on developing embodied multimodal foundation models to power general purposes agents that can act and reason in both the physical and digital worlds. He joined Microsoft after his time as a postdoctoral researcher at UC Berkeley in Professor Sergey Levine's lab. He earned his PhD in computer science from the University of Freiburg in 2023, where he was advised by Professor Wolfram Berger. His work on robot learning has received several accolades, including Best Papers Award at ICRA, at RAL, as well as RAL. During his PhD, he also interned at NVIDIA AI with Peter Fox. With that being said, thank you very much, Oier, for accepting the invitation. We are very thrilled to have you today. So please, the floor is yours. Take it away.
Yeah, thanks so much for having me. I'm really excited to have the opportunity to talk about robot learning and present some of my work today to all of you. And yeah, today I'm gonna talk about embodied multimodal intelligence with foundation models. And so now I'm affiliated with Microsoft in Zurich, where I joined a few months ago, but most of the work I will be talking about comes more from my postdoc and some of my PhD. So to kick off, so my research goal is really to, as many others in the field, to develop generalist robot policies that unlock intelligent autonomy across diverse applications, such as home assistant robots that can work for and alongside humans. And concretely, this means developing novel solutions that essentially generalize to any robot in any scenario, even if the environment is unstructured. As you can see, some from these videos that depict results in the real world from my past works. So the canonical approach I'm taking towards this goal is inspired by advances in other areas like NLP and vision, where there has been this paradigm shift in which we have seen that large models trained on diverse data sets surpass specialist models tailored for specific tasks, like let's say object detection, where we have like RCNN, fast RCNN, and so forth, image captioning, or translation. And the workflow for developing these models, for example, is that in NLP that they train models on large diverse data sets that can then not only do one single task, but many, like code completion, translation, question answering, and so forth. And they typically outperform then models trained for these kind of single tasks only. And if we look now at some of the most impactful advances in robot learning in the last couple of years, we have seen really tremendous progress in, for example, performing dexterous tasks by methods like ACT or diffusion policies. However, these approaches are kind of typically more specialized models that work really well to fit single tasks, but are a little bit more difficult to scale in order to learn more generalist robot policies, as you often would need to retrain these approaches for every new task you want to learn in separate policies. So therefore, really, the North Star of my research is to build this kind of novel workflow for robotics by building generalist robot policies that can control many robots in many environments and perform many tasks while working with and alongside humans. So I can envision a future where you can essentially download your favorite robot brain online, and then out of the box, your robot starts showing intelligent behavior in a reasonable and useful manner for any robot. Okay, so let's talk now about the key ingredients that we need for developing generalist policies and what are some of the differences and challenges in applying the same recipes that have worked in NLP or vision to robotics. So let's start with the obvious ingredient, which is that unlike in those other areas, we typically don't have the luxury in robotics of readily available large data sets. that we can download and train on. Since robot data is scarce and expensive and usually requires human supervision to collect data. Additionally, as we all know, robot data is highly multimodal and very heterogeneous, as instead of only now training just on natural language, for example, we now face several sensing modalities we need to that robots typically need in order to interact in the real world. And depending on the embodiment and the task, well, these robots will have like different observation and action spaces. So it's really very heterogeneous. And another issue is that we also typically need to run our like robot policies at high frequency or real-time frequency at least. So we don't can't really wait for a minute for like like the ChatGPT API to return a response before executing the next action. Finally, as we develop robotic models that can perform many tasks in many environments, we also need better ways of doing evaluations because the more capable your policy is, the higher, the more expensive it gets to evaluate these models. All right, so I'm going to now talk about each of these separate ingredients. Let's start with the data. So where do we get this data, robotics data from? Because no matter the embodiment, collecting data, robotics data is very costly as we need to teleoperate typically a robot to collect data for each and every single task we want to learn. And I speak from experience here. As you can see me on the left, collecting teleoperation data with the Franka robot setup I built during my PhD in Freiburg in Germany. This is why my research has focused on leveraging existing sources of data across existing embodiments. There had been some previous efforts to collect data sets for specific embodiments, like the fractal dataset from Google or Bridge V2, but usually not in a format that was very compatible with each other. However, the key insight here is that typically there actually exists more robotics data than we think of because essentially every like robotics lab in the world typically needs to collect some data to support their experiments. And this might be maybe like a bit niche for supporting their particular research. And this is why they might not like think of like uploading it or making it available for the community, but actually there is much more data than we than we think of. And so when I was wrapping up my PhD, I was able to collaborate with Google on this project called the OpenX Embodiment Dataset, where we essentially ask all our friends if they had existing robot data, and then we aggregated all of these diverse data sets into a common format that enabled training on them. And so we ended up with over 1 million of real robot episodes, which was substantially more than any previous robot data set. And this data set contains not only a single robot, but over 22 robot embodiments. And it was like a huge effort with over 34 research labs participating all around the world on this kind of community-driven effort. Regarding the results, this was the first time we saw sparks of a single model trained on multiple robots across multiple datasets, surpassing the best previous method tailored for a particular setup. And personally, I was one of the 5 researchers and the only one in Europe that contributed continuous evaluations during the model development with the robot setup I built during my PhD in Germany, which you can see on the top. This paper has been quite impactful because it has allowed algorithmic progress on the modeling side of developing generalist policies by making it possible to train over 1 million of diverse cross-embodied robot data for the first time. And most of the works I will be presenting in this talk will also use this OXE dataset as their foundation. Okay, so far we have talked about where to get the data to train a generalist policy. But even if we now have a large diverse data set with several embodiments, how do we make use of this data to actually train models? How can we model this data distribution? Because of course this is easier said than done, because there is a general lack of a shared interface. Different robots may have different kinds of task specifications, different types of sensors, different action spaces, and so forth. And figuring out how to share information and knowledge across robots and tasks that may look so different makes this a really hard problem. So let's start with a basic example. When we typically train a robot policy, the model takes as an input a current image observation from its camera and a task, which nowadays often is a language instruction. Let's say it's pick up the spoon. And then the model predicts a sequence of actions like anti-factor poses to achieve that goal. And now we want to fit our model on a large heterogeneous data set. And so if we squint a bit and replace the robot image with a more regular internet image and replace the instruction with something like caption the scene, and then the model answers like, oh, this picture depicts the Statue of Liberty or something, this actually starts to look quite familiar because it's very similar to a vision language model. And so the key idea that the work I will now show builds upon is that we can view robotics as a very similar problem where we're trying to learn a powerful model that maps from images and instructions to answers, just that in our case, the answers are not text, but robotic actions. So this means that the way we formulate our problem is a multimodal sequence prediction problem, where we have language tokens, image tokens, and action tokens. As a first step towards developing generalist policies, one of also my first works during my postdoc at Berkeley, we developed Octo, an open source generalist policy, where we trained a large transformer-based policy on around 800,000 robot trajectories of the OpenX embodiment dataset by tokenizing all the diverse heterogeneous inputs and action outputs. So how does it work? The Octo transformer is a fairly straightforward transformer model. So it has a pre-trained language encoder that tokenizes your language inputs, and then it has an observation tokenizer that takes care of the image style inputs by patchifying them and running them through a shallow CNN to produce the image tokens. Now the observation and task tokens are concatenated and fed into a large transformer, which actually is very, very similar to a vanilla VAT or vision transformer. Additionally, there is one more part in the architecture where we define these purple readout tokens, which are placeholder tokens that summarize the embeddings that then go to the functional heads. And maybe one thing to note is that we train the model with goal-conditioned behavior cloning, meaning that it learns to predict a sequence of actions to reach a goal state given current state. And this formulation also helps encoding flexible ways of specifying goals, such as goal images or natural language inputs. All right, so we have now the task, the observation, and the readout blocks. And since this is a sequential model, this will happen over multiple time steps. For the functional heads, in our case, we used a diffusion decoding head because we found that diffusion works really well for these kind of continuous multimodal action distributions. We divided the evaluation into zero-shot evals and fine-tuning evals across many institutions where we use the same fine-tuning recipe to adapt Octo to a new sensory and action space. In terms of results, we found that in experiments across, I think it was 9 robotic setups, that Octo can control multiple robots out of the box, outperforming previous models from Google trained on similar data. Now I want to show a video. I don't know if
Can I ask a quick question?
you hear the sound.
Yes, we can hear the sound.
Bam!
Oh, success. Nice. One success. All right, good.
So this video shows, I think, the first successful grasp we ever saw on the Google robot from an Octo model that we were serving to them via a remote server. And you can see how excited we were when it worked for the first time. Although also, the task is not like too complicated. It's worth mentioning that when we were doing these evaluations at Mountain View, when Google was doing these evaluations, that they were doing these evals in a completely different building to the one in which they originally had collected their data, like 2 years ago or something. So it was quite out of distribution, and we were happy to see that our model still generalized to a unseen building.
Oier, can I ask a quick question about the network design?
Yeah, sure.
Well, so you were mentioning the readout tokens. Are those basically just the classification tokens that are used for vision transformers? Or are there something a little more unique?
Yeah, it's just like kind of like embedded, like the summarization embeddings from which then you can project like the actions.
Okay, thank you.
Yeah. Okay, so these were zero-shot evaluations, but one thing I want to highlight is the adaptability aspect, because ideally, the model or in general, like generalist robot policies should be useful for your robot, even if we did not pre-train on it. And it's possible that on some tasks we might want to use, like let's say a force torque sensor, or we might have more cameras, or we want to do now joint control, right? So it should be possible to easily adapt the model. So in this case, if you have a new input, like let's say force torque readings, you can slot in this new input with a few tokens, and then you fine-tune the model, and you don't need to throw away the model weights from before, because most of the parameters of Octo are inside the transformer. You get to retain much of the pre-trained knowledge. And similarly, if you can also create new action heads if you have a new head that you want to predict like a new function, like let's say you want to predict values because you want to do RL, you could also kind of like slot in a new readout head and train on this without messing with the rest of the network. I won't go into the details about the fine-tuning results, but we found that the representations learned by Octo work much better than state-of-the-art visual representation learning methods like R3M, Visual Cortex 1, etc. And in terms of impact, Octo has become quite popular, becoming one of the most downloaded robotics models on Hugging Face. And we also, more importantly, we actually have seen that researchers found it useful for fine-tuning. So on the bottom left, there is a video I found on Twitter of a researcher fine-tuning Octo on a Boston Dynamics spot robot, which is a completely unseen embodiment for the model. And then on the bottom right, you can see a Japanese company that is using Octo to drive their humanoid robot. So that's pretty exciting. All right. So far I have showed how you can train a generalist policy on a diverse data set containing a bunch of single arm manipulation tasks. But if we think about this for a second, this is really a generalist policy if all it can do is single arm manipulation. because as you all know, robots come in many more morphologies, right? And this means that if we could expand quite a bit on the data that we could be learning these models on by leveraging, like, I don't know, quadrupeds, self-driving cars, humanoids, etc. And there is also a lot this potential of having like better transfer of knowledge across these different embodiments, right? So, for example, let's say like navigation data might transfer to drones by learning how to avoid obstacles, for example. And obviously, I'm not the first one to have this idea of trying to use data from different robot morphologies. And related work already showed signs of some transfer, for example, between egocentric manipulation and navigation. But typically, the approaches we found had always some sort of drawbacks. Either it required manually aligning action spaces or restricting yourself to like a kind of very specific camera configuration and so forth. So kind of like it was like not really scalable, I would say, like for any robot. And this is why my research has focused on developing more scalable approaches that can learn from any robot embodiment. And concretely, in this work, we added more embodiments, such as bimanual manipulation, navigation, or locomotion to the data mix we originally trained Octo on, for a total of 900,000 robot trajectories, and trained a big transformer, but with embodiment-specific heads on it. And we call this cross-former. And this model, our cross-former model, accepts variable observation inputs and predicts variable action outputs, which is important to predict chunks of different length to account for embodiment-specific control frequencies. Because here now we have from like 5 Hertz control with the Widow X to like 50 Hertz control with like a Aloha bimanual setup. But more importantly, this model can consume now data from virtually any embodiment, as we don't need to do any manual action space alignment. And in order to maximize transfer across embodiments, we also maximize parameter sharing across embodiments, for example, by sharing the image encoder weights for camera views of the same type. And here are the rollouts from our cross-former model. And as you can see, we evaluated on very challenging tasks, from indoor to outdoor navigation to very dexterous tasks on the bottom left, like bimanual sushi cutting, where like first one hand needs to grasp like the knife, and then like with the second hand, like you have to like start cutting the sushi. So it's like a very long horizon and very it requires a lot of precision and dexterity. And also quadruped locomotion and drone flying. So what I want to highlight from this video is maybe like not so much like the task performance itself, but that all the rollouts you are seeing in this video come from the same model checkpoint. So it's the same like weights that are like driving all these different, very vastly different morphologies. So I think that's pretty cool. And regarding quantitative results, we found that our cross-embodied policy either matches or outperforms specialist policies trained for the specific embodiments. Cross-former has also been quite impactful by receiving broad attention from media and also industry. And additionally, it has enabled a spur in follow-up works in cross-embodied generalist policies, such as, for example, like works from physical intelligence. Okay, so now at this point in my talk, you might be wondering, is scaling cross-embodied robot data all we need? Because it seems that, okay, like all this work kind of rely on having like lots of data, and you train a transformer, and we're kind of done. And the answer, at least for me, is not really, because there is like one big limitation to these policies that I've been talking about, um, which is they don't have intelligent reasoning, right? So even if we develop a robot capable of many tasks, this isn't like that useful if it doesn't have intelligent reason capabilities. So this means that for the models I have shown so far, like Octo and Transformer, if they face an out of distribution situation, they have really no mechanism to intelligently solve it. And we can, for example, again, take inspiration from LLMs, right? For LLMs, even after training on all of the internet, right? So on way more data than we have been training these robotic models on, they are still they are still not able to solve all the problems we want LLMs to solve, right? So even all of the internet is not enough for LLMs to solve all the tasks we want them to solve. For robots where the data is more expensive, it's also likely not going to be enough. So an alternative that has been kind of emerging in the last year is to train for reasoning, because reasoning are compositional bits that can be reused and transferred to solve with existing knowledge. And so in LLM land, people are now specifically training for reasoning, and we kind of want to be doing the same thing for robotics to try to endow them not only with the capability of doing many low-level tasks, but also with intelligent reasoning abilities. And so now, because we are formulating robotics as a multimodal sequence modeling problem and trying to transfer many advancements from LLMs and VLMs, like model architectures, training objectives, and so forth, the question is if we can also transfer some of the algorithmic improvements that have helped, for example, VLMs generalize, such as the idea of chain of thought reasoning, meaning that we make the models reason before predicting the answers. And so to this end, we proposed embodied chain of thought, where we make our robotic models reason through the task at hand and the next actions it's supposed to predict before actually predicting the next action. So this means that instead of mapping directly from images and language to actions, as you see in this video, we now perform what we call embodied chain of thought reasoning steps before predicting these actions. The idea is actually simple. As we want to maximally use the robot data that we already have, we can use internet scale foundation models to annotate our existing robot data by generating semantically grounded reasonings like subtasks, predicting bounding boxes of objects to interact with next, or traces of how the gripper is going to move in the future. Now, the core idea of embodied chain of thought is to train an autoregressive vision language action model that predicts these intermediate grounded reasoning steps before predicting the robot actions. So essentially, what this means is that we are kind of forcing the model to think carefully and look carefully before acting. And on the screen blobs and rectangles, you see the semantic reasoning steps, which happen in language space. So these are kind of more similar to what you might know from LLMs. And then the purple ones are the visual reasonings, which are grounded in the image observations, like predicting the bounding boxes of the object we're going to interact with next, or predicting the gripper traces of how it's going to move into the future. We evaluated our model across challenging out-of-distribution tasks like spatial relations, unseen objects and tasks, and to our surprise found that this resulted in 30% performance boost over OpenVLA, which is the identical model but trained on the same data but without the reasoning steps. And it also performed better than RT2X, which is a closed source model from Google, much larger, 55 billion parameters, I believe, compared to our model, which just had 7 billion parameters. And maybe like the key thing I want to highlight here is that essentially you get this like more approximately 30% performance boost in generalization without having to collect any additional robot data, right? So for the same amount of robot data that you already have collected, you can boost like your model's generalization quite a bit by performing this embodied chain of thought reasoning steps. And another advantage of this paradigm is that not only does this improve performance, but it also makes the robot policies more interpretable, as now you can see what the model thinks of doing, and also more interactive because it also now allows humans to correct behaviors by editing the reasoning chains online, right? So if you see that one of the reasonings is wrong, you can correct them. And because it's like an autoregressive model and the actions are conditioned on the reasonings, then it will also like correct its behavior at test time. So I think that's also very, very nice traits of this approach. And one of the most surprising experiments in our paper was that we trained this embodied chain of thought model actually on just one data set, on the bridge data set, which is with the one we annotated with like all these different foundation models. And then here we are performing inference of this model on unseen robotic data sets from the OpenX embodiment dataset collection. So these are robots and environments that the model has never encountered before, and we ask it to predict like this reasoning steps. And I was very surprised to see that the reasonings are actually quite reasonable. So it seems that it generalizes quite well even for unseen robots that it didn't train on reasonings for. And the explanation for this is that I believe that this reasonings are quite similar to many pre-training tasks that the VLM itself is trained on or are typically trained on. So it's really like the VLM that is driving the generalization of these reasonings. And this suggests that embodied chain of thought might be a good way to scale and transfer robot reasoning capabilities between robots. And in terms of impact, this has been quite impactful by becoming kind of like a new standard to pre-train VLAs with reasoning, as it improves generalization, interpretability, and interactiveness. For example, like a couple of weeks ago, there was also this new release from Google, the Gemini Robotics VLA 1.5. And they also, for example, have incorporated this embodied chain of thought approach to train their VLA. So that's pretty cool. All right. So far, I have showed how to build generalist policies that rely mostly on visual perception. But one can only go so far with vision only. In this example, for instance, if we ask our robot to, let's say, grab a ripe tomato from the shopping bag, it might struggle to do so because it might not really see what's inside the bag. It might not be able to use color to determine what is a ripe tomato due to the self-occlusion. And even if it had a wrist camera, let's say, the robot would actually have to touch and feel the tomato to try to deduce its ripeness. I actually did this experiments where I tried, a pre-trained vision-based generalist policy to try to solve this task, and you can see that it really it fails quite spectacularly, right? It's a very, very difficult task because of this partial observability. And so the question is that given that interacting in the real world is a multi-sensory experience, how can we best enable reasoning jointly over multiple modalities such as vision, audio, or even touch sensing, given that we have data scarcity for many of these modalities? And I believe that leveraging natural language as a bridge across modalities is one potential solution. So in this work that we presented this year at ICRA, we proposed a new recipe for fine-tuning generalist policies like VLAs on heterogeneous sensor data like touch and audio that really unlocks for these policies new cross-modal reasoning abilities, such as asking to grasp the object that feels like a pineapple but is brown. How does it work? First, during the fine-tuning phase, we slot in new observation tokens, similar to how we were doing this for Octo. And during fine-tuning, we now propose two auxiliary losses in addition to the BC loss. First, a contrastive loss to maximize mutual information between views and semantics of the same scene. So this is essentially a clip-style loss. And second, a language generation loss to predict high-level semantics across modality combinations with a cross-entropy loss. This then enables our policy to perform challenging manipulation tasks that requires reasoning jointly over vision, touch, and sound in zero-shot settings, enabling several applications like multimodal prompting, generation of object descriptions upon interaction. So when, the robot doesn't see anything with the camera, but then, kind of feels inside the shopping bag what it has grasped, blindly. And then thanks to touch sensing, it can describe what it thinks that it has grasped, right? So I think that's pretty cool. And also compositional cross-model prompting. Okay. So far, I have talked about the data and the modeling of generalist robot policies. But last but not least, we also need to talk about evaluation. Because evaluating robot policies in general is expensive. And if you ever have done real-world evals for one robot and one task, you probably know what I'm talking about because there are many issues like people bumping into your cameras inadvertently, grippers getting stuck, motors get damaged, and you need to do surgery on your robot, life-saving surgery, and it just takes usually a really long time to run robot evaluations in the real world. So one way to get around it, in my opinion, is to use simulation, as this makes research more accessible to people who don't have the same robot setups as you do. And it also makes the numbers that we then report more reproducible. This is why during my PhD, I developed Calvin, which was the first public benchmark of long horizon instruction following from high dimensional inputs, in which a single agent must solve complex manipulation tasks by understanding a series of language expressions in a row and then generalize to unseen environments. I don't have time to go into the details of the Calvin benchmark, but in general, it's been quite impactful by becoming an established benchmark for the vision and robotics communities, and it's been widely used by industry and academia. Maybe one thing I want to highlight that I think is pretty cool is on the bottom right, you can see a real-world replica built for a sim-to-real paper by some folks at TU Munich. And I really appreciate their effort because, I mean, I also kind of built like a real world like robot setup during my PhD, and it kind of took me almost a year to do everything from writing the teleop code to orchestrating everything. And so yeah, I think it's like amazing that someone found the simulated benchmark like that useful that they went all the trouble to build real world replica themselves. So yeah, I think that's pretty cool. But okay, but the question is, I guess like simulated benchmarks are great to drive algorithmic progress and to prototype things, but in general, as roboticists, like we are typically more interested in deploying our robots in the real world. So we will also want to train our policies on real world data, right? So how can simulation help us there? And especially like during the course of like, for example, the Octo project, we first we learn in a painful way how hard it is to develop such generalist policies that can control many embodiments as the cost for doing real world evaluations really increases dramatically. And so this is why we started a parallel project, which we coined Simpler, that tries to leverage simulated evaluations for policies trained on real-world data. So the hope is that if we can find a way to evaluate our real-world policies in simulation in a way that informs us about how they would perform in the real world, well, then, this is amazing because then we can just sit back and enjoy life while we run a large number of evals in sim. And as I said before, this also has the advantage of making these evaluations more reproducible. So it's really a win-win situation. Okay, that sounds great. And not only are the success rates in a real and in simpler correlated, but this actually also importantly holds true for various distribution shifts, like textures, camera poses, and distractors. So how does this work? The first step in our approach is to mitigate the control gap between simulated and real-world environments to ensure that the policy actions executed in simulation yield comparable effects on the robot's end effector as those observed when executed on the real robot. And this can be done, for example, by performing a system identification on a small sample of trajectories from the real-world dataset. The second step is then, as you probably have guessed, to minimize the visual distribution shift. And this means that we essentially are trying now to match the simulated visuals to the ones observed on the real world. And there are two steps that we perform here. The first one is green screening. So this means that we segment out the interactive simulated assets and overlay them onto the real world backgrounds. And then the second step is texture matching. So this means that we project real world object textures, like the cocan, for example, onto simulated assets. And additionally, for this case, for the Google robot, we also tuned the robot arms. We tuned the color of the robot arm by using real videos. Maybe one thing that's important to highlight about Simpler is that Simpler doesn't give you absolute correlation performance. So if your policy in Simpler gets like, I don't know, 50% success rate on a task, it doesn't mean that it will also get 50% success rate on the same task in the real world. What simpler gives you is pairwise correlation. So if you have two policies, A and B, and policy A performs worse than policy B in simulation, then this should also hold true in the real world. Simpler has also become quite popular. It's kind of been like become a daily driver in many labs that want to also do research in generalist robot policies. I think maybe it might have become a little too popular because we sometimes see entire analysis, VLA analysis papers being written with like 18,000 rollouts in simpler and zero real world robot experiments. So maybe yeah, would be good to also add a couple of real world robot experiments. All right. So to recap, I have presented approaches that that kind of I have presented approaches that tackle the different keys or ingredients in order to develop generalist robot policies. So how we can leverage existing robot data to train cross-embodied policies, how we can endow these policies with intelligent reasoning abilities, and also how we can post-train or fine-tune such generalist robot policies on new and heterogeneous, also like sensory observations, like touch sensing, audio, and so forth, to really try to drive this cross-model reasoning across different sensing modalities, also for modalities for which we might have data scarcity that prevent us from doing like large pre-training with them. And I also have presented approaches in order to ease the cost of evaluation of such generalist robot policies by presenting approaches that leverage simulation benchmarks and also like real to sim correlated evaluations. For the future, I'm highly motivated by developing intelligent assistant robots that can perform tasks for and alongside humans in unstructured environments for extended periods of time. I believe that the four key ingredients we need for that are advances in dexterous mobile manipulation, intelligent embodied reasoning, lifelong learning, and also rapid adaptation at test time. And with this, I want to finish by thanking my fantastic collaborators, without whom much of this research would have not been possible. And thank you for your attention, and I'm happy to answer any questions you might have.
Thank you very much, Oier. Great presentation. We'll open the floor for questions now. Go around or online. Feel free to ask.
Yeah, I'll ask a question, or I'm really curious about like the gap between the state-of-the-art generalist models, like with reasoning that you talked about, and what we would need for like carpenter level spatial reasoning, like this idea of, let's say you have a task which is cut 12 pieces of wood each 3 feet long, which kind of ties with like what you're talking about at the end. And that's something that because I love construction, I'm kind of like in both worlds. That's something I'm always like been wondering about recently. Like if the robot has to measure, keep count over multiple steps, and plan its actions in 3D space, like have you tried tasks in this vein? What have been the failure modes? Like, and then even just thinking, what do we need to do? Like, what do you think are the most promising things to explore? Do we want like similar to what you were talking about, integrating touch and audio? Could we integrate LiDAR, like, or just have the robot get a tape measure and just measure it? Like
Yeah.
So
Yeah, that's a great question. I think so. I think there are like multiple things that I think kind of we would need to work or improve upon to address these questions. I think uh, probably like the biggest issue right now is that like the large foundation models that we use as backbones to develop like robot foundation models, like so the today's VLMs typically don't have a good like spatial intelligence or physical grounding abilities. So this means, for example, they don't have good like depth understanding, right? So these are, for example, things that we are looking at now at Microsoft, where we're developing new frontier models and trying to improve their spatial intelligence capabilities. I think another issue that probably is also relevant is like memory, right? So in your case, if you have like a manual with 12 steps or something to build this or to assemble your like carpenter level um, like I don't know, furniture or something, it's very easy for the model to kind of like get lost or like forget about like what step are we on or understand like looking at the what you already have like built or it has built like um, what have I done and what do I need to do next kind of. Does that make sense?
Yeah, totally. That's cool. Thank you.
Thanks for the talk. Amazing body of work. I had a quick question regarding the reasoning work that you mentioned. I vaguely remember work, I think it was from ASU in the language context where they showed that sometimes you could have like the wrong reasoning but the correct answer, right? So they developed a way to like verify if the reasoning was correct because they had rules and stuff like that. So sometimes the model could like output a reasoning that made no sense, but still get the right answer in the end because it's like, autoregressive decoding. So I was just wondering if you had like experience with this. Like, do you feel that these models always output like a reasoning that's consistent with what they do? Yeah.
Mm-hmm. Yeah, that's a great question. I think this depends a little bit on like the concrete like training paradigm that you use to learn the reasoning. Um, like in our case, how we trained original embodied chain of thought, it was like a very simple like autoregressive decoding, right? So there was like no flow matching head or anything. So the action tokens fully were conditioned on the reasoning tokens. So it kind of like usually followed what like the action tokens are kind of mostly followed what the reasonings were. But you can also like use different training paradigms also, right? You can, for example, also use dropout and things like that, right? So then it might be the case that, it's not like as hard of like a conditioning on the reasonings to predict the actions. Does that make sense?
Yeah, that's it.
Yeah.
And yeah, I'd just like to hear your take. Everyone these days is trying to cast their work as doing world modeling. It's like a very trendy thing these days, like world models. Yeah, what's your opinion on this big trend? I don't think you listed this in your future work section, so I was curious.
Yeah. Yeah, I think it's an exciting paradigm, for sure. I think maybe more than world modelings. I'm very excited about video prediction models. I think because they have like great potential in so many ways, right? In terms of that, if you have like a really good video model, like you essentially can do planning, right? And also maybe like another aspect that I'm excited about for video models is that I think because right now we are using VLMs as the backbones, and VLMs are typically trained on, kind of static snapshots, right? Images and captions from the internet, right? Which are all kind of disconnected. They don't really have a good understanding of like real world dynamics, for example, or physics, right? Which then kind of results in this paradigm where in order to train a VLA on top of a VLM, we kind of need like tons and tons of data of like robot teleop data, right? So, we see like, I don't know, like all these like startups and so forth, like collecting huge amounts of data to post-train a VLA, right? But I think maybe like if we are able to train good video prediction models, because they already kind of have implicit dynamics learning inside, we might be much more efficient and might be able to achieve like also good performance for robotics control with way less data that we need with like a VLA paradigm. Does that make sense?
Yeah, that's interesting. That makes a lot of sense. Yeah. Yeah. Thanks.
Yeah. I think there is one more question. I'm not hearing anything, so sorry.
Yeah, I think that's it. I don't see more people asking questions, so to respect your time as well, I think we'll cut it there.
Okay.
Yeah. So thank you very much, Oier, for coming. It was a great talk. Thanks again for accepting the invite. Keep in touch. We'll be in touch as well. All right.
Okay. Thank
Thanks
you
so
for
much.
the invitation.
Thanks so much.
Take care of yourself. All right.
Bye.
Ciao.
Thanks again.